was about the question 9, which is said that prove that Z8Z is not cyclic. Now, I'm not sure, like is like how to prove that other than just sort of like going through the classes from 1Z to 7Z and show that basically they all within 2 or 3 cycles or within 2 or 3 powers they all end up with modulo 1, and so they're not going to generate the rest of the classes. Is there a other way than what I just described?
No, I mean this group, the multiplicative group.
Are you taping, Professor?
Yes, I am.
Thank you.
It only has 4 elements.
Oh, so
there are only
sorry,
4 elements to look at, and for each of these elements,
so
if x is equal to 1, sorry, if x is equal to 3, 5, or 7, then x plus 8z squared is the identity.
Right. So
the group with no element of order 4.
No. So my confusion was simply this: that Z-8Z, does that refer only to the reduced modulo system or complete modulo system?
So where it says Z mod 8Z with the time sign, that means the reduced residue system. Always.
Oh, okay. So I thought it was like it just eliminated 0, not just 0, but all reduced. Okay.
No.
Understood. Understood. Thank you. So while we are in the same section, question 1.2b, which says let R be greater than 0, and then the description of the circle on a complex number. And it says that prove that for R not equal to 1, TR is not a subgroup of CX. So for that, can I simply use the fact in the part 1a where we prove that if it's a unit circle, it is for the unit. It says if it's a unit circle, we know it's a multiplicative group, and one of the part requires to find inverse. So can we just use that, showing that the inverse will have a radius or will not satisfy the equation for the radius? It will be 1 over R, which means it's not part of the group.
That's one way to do it. An easier way to do it is that the multiplicative unit is 1, and 1 is not in TR if R is different from 1. Because
that was another way I thought about it, right? So either of those two would be sufficient, right?
Yes.
Question 5, Professor, prove that the congruence class A plus MZ is generator of ZMZ if and only if A is relatively prime to the M. So for the, I'm having some trouble with the if and only if part. If A is relatively prime, I can show that AX equal to B has a solution, a unique solution for all B from 0 to from 1 to M minus 1, which means that A times A plus MZ is a complete system because of that. How do I prove the reverse?
Well, so let's see, which number was this?
This was number 5.
Okay. So number 5. So if the greatest common divisor of A and M is some number D, which is at least 2, then let's see this one. So this is an additive group. So then n times a plus mz, which is na plus mz, is never equal to 1 plus m, never equal to 1 plus mz. Because na congruent to 1 mod m has no solution. If a plus mz were a generator, then every element of every congruence class would be a multiple of this element of this congruence class. But no matter what n you choose, n times this is never the congruence class 1 plus mz, because you can't solve this. Right? This has no solution.
Okay, so then oh, okay. So basically the proof would consist on two parts, basically saying that let's take two scenarios. One when the GCD is greater than 1, and in which case, as you just showed, that there is no solution. And then the other case would be when the GCD is 1, and you show that n is simply n times 1, which would be a plus mz.
Correct.
Okay, understood. And the converse is basically to show that
right. So you can also do this in a slightly different way. So here's an alternate proof of this version. If a plus mz generates this whole group, then there exists an integer n such that n times a plus mz is 1 plus mz, which means that na is congruent to 1 mod m, which means a and m must be relatively prime, because 1 is divisible by the greatest common divisor of a and m. So that's an alternate way to do it.
Right. Okay. Yeah. No, I was thinking more about the congruence classes where I said, like, you know, ax equal to b is solvable only if the GCD of a and m divides b, and for the only number GCD can be is 1 for b equal to 1 to m minus 1.
Yeah, I mean, it's exactly what I did here. It's slightly different formulation.
So yeah, that's the same thing, I guess. Okay. And in question 7, it says prove that 3 plus 5z is a generator of z 5z x. How do you say that, z5zx?
It's just the congruence class 3 plus 5z.
No, right. No, but I'm saying, like, no, how do we is there a specific way of saying the class is z/mz, or it's just?
Well, you can say the integer is mod 7.
Okay. So my question is this. So when you say that, you know, in questions 7, it says 3 plus 5z is a generator of z5z. Is we always take it as a multiplicative group, or is it also additive group?
No, when you write z mod 5z with the time sign up, that means the multiplicative group of congruence class is mod 5.
Oh, so the cross at the top it signifies it's a multiplicative group. Is that what it is?
Well, what it really means is the elements of z mod 5z that have multiplicative inverses. And in this context, it can only mean, first of all, if you say 3 plus 5z is a generator of something, it has to be of a group. So z mod 5z, that star, that's just the congruence classes 1, 2, 3, 4. That's a multiplicative group. It's not an additive group. So it wouldn't even make any sense to think of that somehow additively. When you use the word generator in group theory, you're talking about an element that generates a group.
Right.
So there's no other group. Z mod 5Z star must be the multiplicative group.
I
It's
thought
not an additive group.
I thought it was both additive and multiplicative.
No. Z mod 5Z has an addition and a multiplication. It's an additive group. It is not a multiplicative group.
Professor, now I'm totally confused.
Well, Z mod 5Z has 5 congruence classes.
Right.
It's a group under addition. It is not a group under multiplication. The subset of Z mod 5Z star is a group under multiplication. But Z mod 5Z itself is not a multiplicative group.
Right. That part I
Multiply,
understand.
but it's
That
not
part
a
I
group.
understand. But so when you say Z mod 5Z star, which is a multiplicative group, isn't it also an additive group?
Absolutely
No,
not.
because I didn't. But sorry, because the 0 is not there, it won't be additive.
And it's
Okay, I
not
understand.
closed under addition.
Right, right. No, I understand now, because we removed the additive identity.
Yeah, you move the 0 congruence class.
Okay.
Can I do my coding?
Are there other questions about group theory problems that I can answer?
Unless somebody has another question, I have a question that's not part of the homework.
All right, just one second. Let me also remind everyone that I keep posting announcements on the Blackboard website, so you need to check it, I would say, at least every day. Also, I keep adding to the notes on group theory. So you should always look at the latest version that's on Blackboard. All right, so if you have another question, go ahead. So you said you had another question?
Sorry, I had muted myself. Yes, I had a question. It's not part of the homework, but I was looking at question 10, which says the Klein 4 group is not isomorphic to Z mod 4Z. My question was, how do you prove something is not isomorphic? In this case, I mean, given that there are 4 factorial, which is basically 24 possible sort of functions that you can generate between the Klein 4 to Z mod 4Z.
Okay, well, that's a good question. Let's see. So this is in section 1.2, number 10, to prove that the Klein 4 group V is not isomorphic to the integers modulo 4. So of course we know that each of these groups has 4 elements. So there certainly are many one-to-one and onto functions from one to the other. So the idea is to say then that it's not possible to have a function. So we must show there does not exist a function f that's, say, from which way should I do it? Maybe Z mod 4Z to V that is one-to-one and onto, and satisfies the property that f of x plus y is f of x times f of y. Okay. See, this is in Z mod 4Z. this is, I'm writing this, I can write it additively or multiplicatively. Maybe I'll write it plus. So this is addition in V. So what can we say? So suppose there is such a function that satisfies this. Then, so f of, so whenever you have an isomorphism, so let me just make a couple of quick sort of notes. So that f from G to H, these are just any groups, be an isomorphism. So if we let, let's say EG be the identity in G, and E sub H, that be the identity in H. And just for simplicity, I write everything multiplicatively because that's the normal way to write a group. So we have, if you multiply the identity with itself, you get itself, right? Like 1 times 1 is 1. So f of the identity is f of EG times f of EG, sorry, is so if you take f of the identity, of course, the identity is the same as the identity times the identity. And using the sort of functional equation for an isomorphism, this is f of the identity times f of the identity. So this element is equal to this times this. Now, over in H, every element has an inverse. So multiply by f of EG inverse. So on the left, you get f of EG inverse times f of EG. And on the right, you get f of EG inverse times f of EG times f of EG. I just took this equation and I multiplied this element, which is the same as this, on the left by this. But here I have an element times its inverse. This is just the identity. An element times its inverse is the identity. This is in H. And this is the identity. So this is EH.
One question, Professor. When you take f of EG inverse, so is that, so that's not f inverse of EG, so right, that's very different thing, right? You're just saying
this is an element.
F of EG belongs to H, and there's an inverse in H for that, whatever that element is.
Correct. That's what this means. This is the inverse of this element.
Okay, now I'm following. Thank you.
So this is the inverse. This is the identity in H. This is the identity in H times f of EG. But the identity times anything is f of EG. So what this says is, whenever you have an isomorphism of groups, the identity always gets mapped to the identity. So you have this function f from G to H, and if it's an isomorphism, the identity goes to the identity. Right? That's this fact. So let's go back to our problem. Let's see if that's all we need. We have a function from the integers mod 4z to the Klein 4 group. So suppose we take f of the congruence class 2 plus 4z. So 2 plus 4z is not 0, right? It's not the congruence class of 0. So f of 2 plus 4z, of course, 2 plus 4z is 1 plus 4z plus 1 plus 4z, right? Because, as you know, in algebra, 1 plus 1 is 2. And because of the functional equation for the isomorphism, this is f of 1 plus 4z plus f of 1 plus 4z, which is 2 times f of 1 plus 4z. This is all in V. And in V, every element, the identity is order 1, every other element is order 2. So 2 times anything, this is 0. This is the identity over in V. So f of 2 plus 4z is the identity in V. But f of 4z is also the identity in V, because this is the identity in Z mod 4z. So I have two different elements that get mapped to the same thing. So therefore, f is not 1-to-1. That's it. Right? So
I didn't follow the part where you said that, you know, I follow that 2 plus 4z can be written as 1 plus 4z plus 1 plus 4z. And then
Yep.
you split in terms of f of 1 plus 4z. But how does that become E of V?
oh,
How does that become?
because in the Klein, I mean, you have to know what the groups are. In the Klein 4 group, if you write it additively, 2x is equal to the identity, 0, or E times H, for every x. So in the Klein 4 group, every element has order 1 or 2. Doesn't matter what element you pick. So whatever
Okay.
this is, 2 times it is 0. If I'm writing it additively, it's 0. So,
Okay.
but 4z also gets mapped to 0 or to the identity. So these are two different congruence classes.
Understood.
And so F cannot be an isomorphism.
Okay.
So that's the proof. So now we're getting into algebra. That is really algebra. It's not just doing some computations. You have to develop the ability to prove theorems.
In terms of question 4, I just wanted to check if my approach is correct. The question 4 says that, you know, prove that 1 and -1 are the only generators in cyclic group Z. So my approach is to say that let's assume there is another generator D, and then show that, you know, D ends up being either 1 or -1, and start with the assumption that D is not one of them. Would that be basically a valid approach?
So for number 4, all you have to say is, first of all, n times 0 is 0 for all n. So n is not a, so 0 is not a generator. And if D in absolute value was greater than or equal to 2, then n times D is never equal to 1 for all
Okay.
n. So
That's even
D
more
is not a
simple.
generator.
No, that's even simpler. So yeah, okay.
I mean, any way that works is fine.
Professor, can I see my graded midterm back, or
Well, all I have is a list of points for each question.
oh, okay. Let me look at my grades. I just wanted to know where the error was.
So send me an email and I'll send back to you your grades for each question.
Okay.
Professor, I had a question about number 1B from today's homework in section 1.3.
Okay, just a second.
Sure.
1.3 is on matrix groups, and question number what?
Number 1, part B.
So 1.3, number 1B. Well, you're just adding matrices. So if you have a matrix A11 up to A1n and AM1 up to AMN, so these are m by n matrices. So they have to have the same shape. We just define addition coordinate-wise. So in general, if we let this matrix be C, like the 1,1 coordinate is A11 plus B11 up to A1n plus B1n and so forth, AMN plus BMN. So to show it's an additive abelian group, you have to show first, so it's clearly closed under addition. There's no problem about that. Sum of two m by n matrices gives you another m by n matrix. It's associative. Because if you look at any coordinate, suppose you're adding A plus B plus C, the ijth coordinate is going to be Aij plus Bij plus Cij. And if you compare that to A plus B plus C, the ijth coordinate is Aij plus Bij plus Cij. And because addition of numbers, real numbers or complex numbers, is associative, these are equal. So therefore, these are equal. You have the associative law for addition of matrices. You have the zero matrix, where every coordinate is zero, call it Z, ZMN, and A plus ZMN. You're just adding 0 to every coordinate, is A. And if you have the matrix A, if this is the matrix A, the additive inverse is just, you just take the negative of all the coordinates. And A plus minus A, what is the ijth coordinate? It's Aij plus minus Aij, which is 0. And finally, A plus B equals B plus A. Because if you look at the ijth coordinate, Aij plus Bij is the same as Bij plus Aij. So all of the properties of an additive abelian group are satisfied for the set of m by n matrices.
Okay, thank you so much.
Sure. Other problems?
Professor, I just have a clarification question for one of the homework problems for today.
Okay.
It's number 6 where it gives you 3 different matrices.
Which section?
This is section 1.3 for today.
Okay.
Just to clarify, where it says show that E12, is it just saying E12 squared? Is that what that
Yeah,
2
3
is?
squaring the matrix.
Okay, all right. Just wanted to clarify that part. Thank
Yeah.
you.
Yeah, it looks like, so each of those matrices has order 2. You square them and you get the identity.
I see. Okay.
Professor, do the midterm grades already include the bonus question, or is it out of 100 or 110, so to speak?
Well, if you got everything right, you would have gotten 110.
Okay.
Any other questions? If not, then I encourage you to study a lot of group theory, and I will be back here tomorrow morning at 11 o'clock. Okay. Bye, everybody.